Field. I'm the Executive Director and CEO of ASME, and I want to welcome you here to today's briefing. Organs on demand. What's stopping us from made-for tissues and organs? Sponsored by ASME and the United Engineering Foundation. And welcome again. Please grab something to eat. ASME, as many of you know, has over 100,000 members globally that works to serve the mechanical engineering profession by advancing, disseminating, and applying engineering knowledge, improving the quality and safety of life globally. It's something that I'm proud to be a part of. From bioengineering and manufacturing to robotics, clean energy, and pressure technology, ASME is in the forefront of every one of these technologies. We've just spent 3 days here in Washington, D.C., or 2.5 days in Washington, D.C., talking about these exciting subjects. And again, this is one that I personally like, and it's a favorite one. So today we're excited to convene some of the most esteemed executives in the field, provide their view on challenges and opportunities facing businesses and organizations in the United States when it comes to scaling up production of engineering tissues. Interesting line, not tissues, engineering tissues. I like that. So with that, I know better than to stand between a great speaker and lunch. So what I want to do is introduce my friend and colleague, Saeed Amir, our president of ASME, to welcome all of you. Thank you again.
Well, good afternoon, everyone.
Good afternoon.
For those of you who, this is the first time you were in this room, this used to be called the Gold Room. I think it's called the Gold Room. The last time I saw it, it had gold curtains and gold curtains on this side. And I think the curtains were like 200 years old. And the carpets were ripped and the audio visuals were pretty bad. It didn't have the technology. I'm really glad that it has been renovated. It looks like a real good accomplishment now. Well, it's really my great pleasure to be here and welcoming you to today's briefing. As my friend Tom Constable said, the title is Organs on Demand, What's Stopping Us from Made-to-Order Tissues and Organs. He's right. I'm going to be ready and need one of these very soon, so please hurry up. ASME promotes engineering and physical sciences in the U.S. and around the world, and today we will hear from a panel of experts about the potential of such advances in bioengineering that will completely transform our efforts. I should add that this briefing is convened in conjunction with the House Manufacturing Caucus and sponsored by ASME and the United Engineering Foundation, AIME, AICNG, ASCE, and IEEE USA. And I'll just also have to tell you that it's a pleasure that Manufacturing Caucus is sponsoring this. The 2 years I was here as ASME Congressional Fellow, I was managing the House Manufacturing Caucus jointly between Congressman Tim Ryan's office and Congressman Tom Reed's office. And unfortunately, we're not sure if they can make it. They usually try to come here and spend some time and say a few words. But we'll see. There are things happening here on the floor. And it's really unpredictable at this point. And I do want to recognize Casey, who is an ASME Congressional Fellow from Congressman Reed's office, and Andy Ingo, who is a former ASME Congressional Fellow from Congressman Reed's office. Is anyone here from Congressman Tim Ryan? Not yet. Anyway, so someday you guys will be developing and creating bones and organs from 3D printing or other technologies. And these contributions will have a profound impact on patients, all patients. So before we go to focus on the potential that new technologies will have, we must also remain cognizant of the many challenges that still stand in the way of being able to simply just get online and order our new tissue. It's going to take time, it's going to take a lot of R&D funding. Believe me, it's not going to be inexpensive, and it's going to require a lot of talent. It's going to require a new talent with new skills and new ways of thinking. So there has to be focus on education and workforce development for this technology, as well as other new technologies that you have heard about. I have to tell you, and make a note, that the presentation you will hear today represents the views of the presenters who are experts in the field, and these views are not necessarily the position of ASME. Our counsel makes sure I include that. And maybe I have to tell you, but he hasn't said this, the exits are here and they are more clear in case of emergency. We are privileged today that we have absolutely outstanding animals. And we've been told that initially that we expected to have Congressman Reed to come and talk to us, and also Senator Shaheen, but we're not sure. Is she able to come today? Okay. Yeah, there's so many things going on both sides of the hill today, and that's why you see so many people walking around the hallway asking for more money. And it's going to get worse in the next couple of weeks. These buildings are going to be bombarded by people like us, that we want to tell everyone about how important it is to support what we do. Of course, everyone has good causes, and everyone is doing the same thing. I think once we added all the money that everyone is asking for, it came out to be 3 times the budget that the president had asked for. And so it's not an easy job. So with that, I want to introduce to you someone who really doesn't need introduction. Dean Kamen, who is the Executive Director of the Advanced Regenerative Manufacturing Institute, also known as ARMI, or Army, and also known as BioFab USA. Dean is an inventor, entrepreneur, and a tireless advocate for science and technology. He holds more than 440 U.S. and foreign patents, and many of them for innovative medical devices. He is also founder of DECA Research and Development Corporation, a company aimed at developing internally generated inventions as well as providing R&D for major corporate clients. And he started first robotics, or I'm sure almost everyone has heard about FIRST Robotics and the impact that FIRST Robotics has had on students to get them excited about engineering. And I don't know if you have kept track of the success as to how many students have actually gone and have been encouraged to go through engineering as a result of this. And I know that the numbers are in hundreds of thousands. So thank you for doing this. And I understand, I don't know if you're going to mention this or not, I understand that this program is now international, has been international for at least a year or two. So please join me in welcoming our friend, Dean Kamen. Dean.
So I won't mention, but I do keep track of how much we're doing. I won't mention that this year we have 72,000 schools, $200,000 in revenues. We have, throughout March Madness, we have, let's see, 173 cities holding their regional events. I won't mention that you are invited to the Astrodome on the 17th through the 20th of April. I know we expect 60,000 people to be there to celebrate Brooks' event. Or 3 days later at the Cobo Center, when the other half of the country has been having The only reason I'm making that point is, believe it or not, Army and First have a lot in common. I just don't take the same 30 years to grow Army to be as successful as First is, because we don't have 30 years to wait to turn regenerative organ manufacturing into reality. But I think we learned a lot in how we did First, and Army's moving much faster already. They're similar. They're both not-for-profits. They're both organizations that my entire role in each has been a convener. I tried to bring world-class people, companies, visionaries together to do something that most people would say, this is beautiful. 30 years ago, people said you'll never get 3,700 corporations and tech companies to adopt other people's kids and devote so much of their time and passion to turning technology into an exciting sport. They were wrong. You give people a clear vision, you remind them of the importance, the critical need to have more scientists and engineers running around, and serious people rise to the occasion. With that as background, and some of you that may not know what Army is, a couple of years ago, and by the way, I want to thank the Department of Defense for being one of those visionary little organizations. A couple of years ago, we were told that there was a serious commitment made by the federal government of the United States to solve the problem, particularly the military, that need, because of what we ask these young people to do, they need skin and chrome and carbon and organs. I have been working with DOD, Department of Atheistic Limbs, we've done other things. But we were told the DOD was ready to make a serious commitment to turning the dream of manufacturing replacement human organs to reality. You would think that the federal government of the United States that wants to do something that is as clinical as that would be doing it through NSF or the NIH or all sorts of medical schools. Nothing against them, by the way. They funded for decades all the stuff that has made the science a reality. The amount of knowledge from genomics to proteomics to computational biology, the amount of amazing knowledge that now exists due to government investment in field science is astounding. But a couple of years ago, I was literally at the Pentagon talking to very senior people, and I said, you know, those other government agencies are going to continue to push the boundaries of knowledge. But I don't think any of them are going to fund the activities to create an industry. That's not what they do. And they said, look, the DOD, we buy stuff. We need these organs. So we're going to fund a program to essentially pull that stuff, that science, out of the laboratories. Let those guys win Nobel Prizes in medicine. Let them get their tenure. Let them explain the miracles of biology and medicine to us. But let's get the engineering community organized to build an industry to make organs. And I said, I would give it a shot. We answered an RFP, and I'm very proud to say the Department of Defense said, you know, we're going to come up with $80 million to jumpstart this thing. They told me I need to get it matched dollar for dollar by industry on the requirement. And very, very quickly, very quickly, in 2 months, I went through this. I didn't get 80 million in commitments. I got 214 in commitments. And I realized that to the statement to the world of how different this would be than more medical research. I wanted a company that is not known for prowess in the medical industry or in biology or medicine, but in bringing things to large scale, high quality. So there's only one Fortune 500 company I know that has the word elimination in their name. It went to Ray Perret, the chairman and CEO of Rockwell Automation. I said, look, like the reason that we take the most sophisticated machine people can buy, a car, it's got hundreds of computers in it. Your life depends on it. And a beautiful, well-made car that will last 10 years costs less per pound than a hammer. Or we all buy a little device full of transistors. There's 4 billion transistors in the processor of this thing. They're simple, safe, reliable manufacturing process. They can sell you 4 billion transistors for a couple $100. I said, Blake, those are engineering achievements, not scientific achievements. Yeah, Shockley and Bardeen won the Nobel Prize for telling us how the making works. In the 1940s and 50s, they gave us the science that built the semiconductor industry, but it took the ecosystem that became Silicon Valley to put together enough resources to make super high quality, low cost stuff like this. It took the infrastructure and the ecosystem of Detroit for 100 years to bring us cars. So where is the equivalent of the Silicon Valley of biofabrication? In many ways, it's an even more sophisticated manufacturing process to design and build human tissue, make it consistent, make it reliable, make it affordable. How do you do verification, validation, process control? That's not medical. Shockley and those guys didn't make integrated circuits. They gave us the science of semiconductors. So Blake said to the beginning, you're right. Companies like Rockwell help make the automotive industry efficient. We help build the semiconductor industry, and you're right. There's a huge need, and we can bring to the table tens of thousands of engineers, millions of hours of expertise in building consistent, high-quality stuff. It was such a good sell. It was the first one I read to my outside. I said, you know what, Blake? Maybe you want to be on the founding board of Harvard. You agreed to do it, and you agreed to become a major partner, and you agreed to help me bring the rest of the industry to the table. I can tell you that it's been less than 2 years since we started, and we now have 132 members, 132 different organizations that are members, a few of which are medical folks, of course, but there are engineering companies, engineering schools, they're doing every aspect of what it's going to take the miracles out of these petri dishes and role models and turn them into large-scale manufacturing of solutions to people in waiting orders. So, Greg, who was at our little institute in New Hampshire, has a couple of slides. That is the mission statement, and notice it's not medical. It's about bringing scale. So for all of you that are new to this, it's not, I'm not trying to tell you what Army is. It's more important for you to know what Army isn't. We're not another basic research institution trying to understand and unlock more of the secrets of life. Trust me, there are brilliant people at every major med school that already have some of those secrets well enough understood. They're ready for prime time. You got to get them out of that environment, out of the environment of science and into the realm of engineering. And to get it to scale, like everything else, you need standards. We need ASA, we need IEEE, we need NIST, we need the FDA. You can't run a big industry. Can you imagine electricity? But you never standardize the outputs. No industry will ever grow unless it's backed up by all the stakeholders, from the users to the inventors, to the developers, to the manufacturers. And there is nothing like that yet, or there wasn't, for the manufacturer of replacement human organs. To prove, to put it into your head of how shocking that is, this is one of those unbelievable pictures coming out of MIT and Harvard and the Continentals. The good news is they knew so much that they could implant in the back of a rodent, the mouse, the right stuff, and it would grow a human ear. This was the cover of every magazine in science and science fiction. Here's the problem. That picture was published in 1997. That's well over 20 years old. How many organs are now being manufactured for people that need them after 20 years? None. But there's a lot more of this going on. There's a lot more organs than just ears. Every major med school is working. You can make neurons now. You can make nephrons. You can make islet cells. You can reproduce the functionality of the pancreas or the liver or the kidney or the lung. But they're all doing it at the scale of a petri dish, under a hood. They're doing 21st century science, but if you visit their labs, Madame Curie would be home in that lab. got a table full of beakers, they do it one at a time, they got slave labor like grad students and postdocs doing this one at a time. It takes them 2 weeks to make one of something, they can't make another one just like it anyway. You don't build an industry that way. You get those people to hand over the recipe for the magic to engineers that understand process and understand manufacturing, that can do it in closed systems and make it reliable. You get the government agencies like this and FDA to help you create the standards so that everybody can do this. So, next. This was one of the slides we gave to the people that reviewed our proposal when I said, yeah, we're gonna create Army. We named it Army appropriately because it was the Department of Defense that's funding it. I didn't want anybody to forget that. So we called it Army, but with an I, advanced regenerative. When you say the word regenerative, everybody thinks you're going to follow it with regenerative medicine. No, it's Advanced Regenerative Manufacturing Institute. And we did this, and we showed them that, look, other government agencies have been funding basic science and research for decades, and they do a fantastic job. And once you de-risk something and you have the formula for how to do it, like drugs that have blockbuster capability, there's lots of money that comes from industry. But something is high risk and unknown and all the time to develop as, go ahead, manufacture. Create an industry that manufactures organs. Venture capitalists don't have the patience for that. Big industry doesn't do that. Pharma doesn't do that. They're about magic glue and bottles. The engineering companies can't do it. So we said, the shape of that curve is why this industry hasn't grown up the way the semiconductor industry did, or the automotive industry, or the aerospace industry. So we said, we'll fix that. Now, one of my thoughts was, they'll never believe that we can create a whole new industry from scratch, especially headquartered in New Hampshire. So we had to get around to that. That's a picture actually of what's now my office. I moved up from New York to New Hampshire 8 years ago and started our little R&D business. But what people don't know is this mill yard, known as the Amoskeag Industries, started in the 1830s to automate something that was done by hand until then. People knew how to make fabric almost prehistoric. The first industry in the world to make a rope. But it wasn't until they automated the ability to run looms and knitting that it became a global industry. And in those mills, from the 1830s to the 1870s, was the largest single operating industrial complex the world had ever seen. And it was the Amoskeag Industries. Now, after 50 years, it became a commodity, it moved around, and now you buy 12 sets of tube socks for 99 cents, made in places. And the mill yards closed during the Great Depression, and they were empty when I moved to New Hampshire. But, next slide. That's what 22,000 mill machines looked like when the Amoskeag was at its prime. And I went and said, look, this little community was once the world leader in a new industry. We can do it again. We'll create another new industry. We'll create the basis of manufacturing human tissue with all the associated sub-industries necessary, all the engineering disciplines necessary to make it a reality. Next. Next. So, I didn't make this headline. You guys down here in Washington put it out. They colorized that picture and made a whole article even before we started Army about all the new technology that's coming up there. So you might snicker at, we're going to turn Manchester into the Silicon Valley of manufacturing human organs. But Silicon Valley was a small, rural campus 60, 70 years ago. Silicon Valley appeared because all the pieces necessary to transform the way we live or the digital world came together in one place, and they allowed that industry to emerge. And I think where we sit now with the 132 members we've attracted, we will do the same thing. Next. So here's an example of what we've got to do, which is bring all the skill sets together to make this stuff happen. Next. So This is far from a detailed flow sheet, but you got to get cells from somebody. And the reason we say cells from somebody is even now, what's proven to be so powerful in giving people replacement organs is virtually all donor organs. Now, what's wrong with using donor organs? Well, there's a couple 100,000 people on a waiting list for kidneys, lungs. 25% of those people die every year waiting. When an organ does arise, sadly, because a 22-year-old person with elderly kidneys slid on the ice under a plastic 4 o'clock in the morning, you better harvest that organ quickly. You better get it to where it's needed. This is not a safe, efficient way to make things work. It's helter-skelter. You do get the organ. A reasonable percentage of them get rejected by the person to whom the organ is planted. If it doesn't get rejected, it's because the person that now has that transplant is going to be taking immunosuppressants probably for the rest of his or her life to prevent themselves from rejecting that organ. And if those immunosuppressants work to prevent the rejection of the organ, it also suppresses their immune system so that things that don't bother you or I too much, like a cold, might be catastrophic. And by the way, it's expensive to stay on those drugs for the rest of your life. So we said, as long as we're going to do it, why don't we schedule somebody that might need a new kidney or liver or lung? Docs know what's going on. We're going to start to have end-stage renal failure. Okay, we'll go collect some of your cells. Part of our automated process, maybe through fully integrated bioreactors, will grow enough cells that while maybe with 3D printers or otherwise we print a scaffold, then we'll grow your organ for you, custom. You'll show up on a schedule to have a surgeon put that organ into you. And you'll go home with a replacement of your kidney or lung, and it will be a replacement from the original equipment manufacturer. No rejection. You just got your own organ back in you. We do it with cars and start motors and generators. I don't want to, can't do it. So we said, that's going to take a lot of work. And then we got to scale it up, and we got to make it reliable. And we got to do all of these things, including figure out how to get it quickly and efficiently, because it has a short shelf life, to the people that need it. So every aspect of what it would actually take to credibly create the industry that will make all these organs is what Army is setting up to do right now. We're assuming the science will be delivered by that group. We'll assume that all the other engineering disciplines that are necessary to focus on how do you do this with living tissue, we are assembling among these members, and we intend to get it done as fast as humanly possible. And by the way, those of you that question that it would be a sustainable industry once it's going, think about the following. We all think, oh, the semiconductor industry, that's a big other. 20% of our GDP is healthcare. And almost all of our healthcare budget is giving people the chronic care because we don't have a solution or a cure. You know, there's only a couple of things that happen in healthcare. You get a terrible kind of cancer that's there's no known cure. It's a tragedy, but it kills you. Very efficient. And at the other end, you get a terrible condition and modern science and medicine, they give you that shot, they cure it. That's also very efficient. Then there's that stuff in the middle. You haven't figured out how to cure it yet. We can keep you alive. We can put you on dialysis every day. We can't give you a new kidney. Well, the chronic care, giving kids insulin because they have diabetes and we can't cure it, but we can treat it. The treatment is almost the entire budget. And take one condition, I know it because we shipped 600 million cassettes from dialysis, and we've been doing it 20 years. Dialysis, end-stage kidney failure, renal failure, is a pretty small group of our population. But the intensive cost of giving these people dialysis, direct cost of dialysis last year was over $48 billion, and including the indirect submorbidities of it, it's over $100 billion a year to take care of 1.4% of the population. It's unsustainable. Now add taking care of people with liver failure, other failure. If you just could make kidneys, if you could just make lungs, if you could just make liver, any one of them would create an industry bigger than what you could imagine. And if we do it right, the core technologies that they each need. Once you figure out how to make semiconductors, you can make video games, you can make computers, you can make memory, you can make processors. Once you have an industry, the specialties are relatively straightforward. If we build the core technologies here, that allows the engineering resources to do it on their own. That's why they need to be doing it. And then we have a few of the big guys, like Rockwell, and you'll see a few others, that can bring to the table the capability to scale. And then we have academic institutions, and we have not-for-profits, and of course we have the Department of Defense, a very nice partner to have. They've got guns. So this is where we are today. I'm not going to get into the details of any of the individual things that we've done over the last 18 months. I'll just tell you that by the end of the year, the all welcome to come. We're having another one of our meetings. We've been meeting all our members as we expand since we started. And in the first few meetings, you can tell a lot of the clinical people are saying, what am I doing here with a bunch of engineers? And you saw a lot of engineers saying, I'm an engineer, I don't know what these guys mean about magic cooling at Petri dishes. But by the end of the first day, like the docs are saying, one of those engineers say they can easily do this. And the engineers are saying, I can't believe those guys know all of this and they do it manually. And all of a sudden, we're getting tremendous excitement and cooperation. So we decided, before even any of the companies go out and do their thing, we're going to make a demonstration standardized foundry. The foundries, we can make stuff. We said, we'll build a closed system in Army at our headquarters that you can put cells in the front end, and in a completely closed system, without the pipettes and Petri dishes and masks and hoods and slave labor and variability, we'll let stuff track along and come out the end in a way that we know what we got, it's verified, it's validated with process control. And I should mention, one of the earliest people we brought into Army, even before we got anybody else, was Richard McFarland, who I believe is here somewhere. We're trying to recover him. He's a recovering bureaucrat. He was an MD, PhD researcher at a major medical school, left there 20 years ago, 19 years ago, spent 17 years in policy at CBER, at the Food and Drug Administration. We said, look, besides getting industry standards, we need the FDA on our side of the table. We can't build this stuff, throw it over the fence and say to them, trust me, I'm building organs. Richard McFarland resigned from the FDA and agreed to come up to New Hampshire as pretty much the first senior guy we had to help organize and convene this group. And through him, we've now got people at NIH and NIST, and of course, like you say, government, DOD. And as I said, our early support among the industry was Rockwell Innovation. So we've collected key people in every field, every stakeholder, every contributor that's going to make this thing an industry. They're all part of it. It's getting more exciting every day. And to prove that I'm not just typing it up, we asked the representative of that giant company, that our poster child company among the 132, Rockwell Automation, to be the next person to tell you we're really not crazy. We're really going to make an industry here, and you heard it here first, folks. So where's David? David, why don't you come on up and convince people that we're not nuts?
So I'm Dave Best, I'm Director of Advanced Technology at Rockwell Automation. Rockwell Automation is the world's largest company dedicated solely to industrial control of information. Dee and I were having a discussion before. Dean is not crazy. Dean has crazy ideas. What differentiates Dean and what he's involved with is the execution. It's just amazing how well he's able to execute and actually make these crazy ideas happen. We're just so glad to be part of this. You mentioned that you approached Blake about joining, and this is a no-brainer. This aligns with our vision of expanding human possibilities. So this was really a great opportunity for us to be part of this, and this is part of our mission. So Dean talked a lot about scale, and if you look at this diagram here, a lot of the work now being done in biomanufacturing, biomedical work is in the laboratories. It's artisanal. It's people doing some great work within the petri dish, and it's not really scalable. Rock automation can't do any of these magic recipes for anything, but we're good at scaling, taking stuff from the lab or the kitchen and bringing it to scale. So there's an example here of a baker. There's these cottage industry of bakers all throughout the United States. And they'll simply decorate cookies, and they may spend 10 minutes on a cookie. And a cookie may take 3 minutes to build. It may take very nice, like $3 or $5. But it's very low volume. It's very high cost for the cookie. There's limited economic benefit. The person may be able to support themselves, or likely it's a part-time job. So our jobs created here. But if you can scale this technology, it's really about bringing this to scale, taking it out of the lab, bringing it into food manufacturing, there's the opportunity. And if you look at what's required to do that, it really isn't that different than things that we do in manufacturing today. If you look at the manufacture of soup or any kind of food and beverage products, there's a need to manage fluid flows and temperatures and pressures over time period and do data analytics and measure what's happening. That is similar to what's happening with biomanufacturing. Those same techniques can be applied to make that transition and to scale that. And that's the only way we can reduce the cost of these. But that's going to be a huge economic benefit, just like Dean was talking about. There's going to be thousands of jobs created. There's only so many people that, so many research scientists out there. A lot of these lines you look today, if you look at the lab, you look at food production, they look the same. You have teams of research scientists maybe producing a couple hundred samples per year. There's no way you can take that and scale to the need. The need may be 500 times as much. You're not going to hire 500 times more PhDs to do that. So how do we make this transition? What we've been working on is actually working with the research scientists early in the program. We actually developed a podcast series. We have somebody embedded on site at Army that helps with podcasts and helps with teaching people. And we try to take things in medicine and relate them to manufacturing. Just like you have a brain, you have a nervous system, and that controls your body. That's very similar to a controller and sensors in a factory. Use the sensors to see what's out there, what's happening. The brain or the programmable controller controls the operation. Or we take and we equate the musculatory system with the motors and drives that control the motion in the factory. The same with the circulatory system. That's similar to pumps. The heart is similar to a pump. There's valves that throughout the body. That's very similar. So we're able to equate these things. And then we work to try to get production equipment into the hands of the researchers as soon as possible. Because they go through, like Richard's working to help them get the validation. If they get the validation on that petri dish in the lab, and they go to then try to mass produce it, they have to start over from ground zero. It will take them years, probably at least 3 years to collect the data using the new equipment, go back to the validation. And that's too long. It's a waste of their time to do it when they have something that's working that could be benefiting thousands of people. We have to make that transition quicker. So those are really the 2 parts we need to do. Get that equipment into their hands, make sure they understand how to do it, and then work with manufacturing engineers to make that happen. We work with somebody that has a great recipe for cookies. We don't expect them to develop a manufacturing line. We put something in place to watch the process, to see what they're doing, to be able to scale it and help them make that transition. And we need to do the same thing with manufacturing. Now, there are technical hurdles that still exist. The measurement science is one of the biggest ones. Actually, having the low-cost sensors we need to make these measurements
to actually do the scaling. We're lucky, we have probably the best measurement science institute in the world, the National Institute for Standards and Technology. Does remarkable work there. I didn't see Tammy involved, I know she's a strong supporter of trying to actually increase the funding for the measurement of the biological sensors have been, that would be a great compliment to actually build that up. They have better fundamental sensors there, and then be able to take those and scale those and use those in production to have these low-cost sensors we need. The other part is the validation of the process. I know Richard's doing a great job being on both sides of the fence. He's able to look and say what really needs to be done and work with the researchers. And when they're collecting the data, they're providing the data they need to the FDA for approval. We need some help making sure that process goes smooth, we're able to accelerate that process, and particularly the revalidations as we do process improvements, which are just part of digital transformations and moving forward. Being able to do that is a big help. And also, as they're going through, looking for ranges they need, they would actually deliver the product they're looking for. So not just a point solution, but look at the range of variables that would still provide viable tissue, viable organs going forward. So these are great opportunities going forward. We're really excited to be part of this. We want to thank everybody who has supported the programs of Manufacturing USA, the programs, particularly the Army Biopack program itself, and helping to fund this. We're going to be part of this going forward. We're excited, and I want to thank you for allowing me to talk to you today.
Thanks for having me today. I'm John Rowley. I'm the founder of Rooster Bio, so the name is my fault. I apologize. I apologize to the company all the time, but we're right up the street in Frederick, Maryland, at the end of 270 corridor. And so I am an entrepreneur as well as a biomedical engineer, and I've been doing tissue engineering work since 1993 when I first started doing it as an undergrad in a lab, right? I was also an entrepreneur during graduate school, and I learned very quickly that I build stuff and it costs a certain amount. I need to sell it for more, right? And if I can't, if my manufacturing costs are too high, I'm not going to have a viable business. And I was trying to supplement my income during graduate school because we really don't make that much at that time. But then also, I was doing tissue engineering research, as I said. I went to a tissue engineering startup. This is 1998 in Cambridge. I was at the University of Michigan at the time. And this company was trying to do an injectable cartilage for pediatric indication. And you just couldn't manufacture the cells. Maybe not half, but a significant portion of the manufacturing lots never made it. The cost of manufacturing took 6 to 8 weeks just to get the cells to expand. And they were way too expensive. And that is when I realized, right, that tissue engineering wasn't going to make it anywhere until we got the cell manufacturing worked out. Right? So I was not an academic person, so I did not stay in academics after my PhD. I went into industry, and I really committed my professional career towards, essentially I call it the commercial translation of living cellular technology. Right? So I've been working on this, on really the cell manufacturing aspects. I'm here to kind of explain why stem cell manufacturing matters. Because stem cells are the most critical, it's the living functional component of these engineered tissues, and also the major cost driver. And I realized until that was worked out, tissue engineering wasn't going to go anywhere as an industry. And then once I realized that we finally got the industry to the cell manufacturing technology to where it is to support tissue engineering, that's when I founded Rooster Bio about 6 years ago. So we take a different approach towards thinking about living cells. We see them not just as tools for basic research, but as technologies, right? It's very similar to a transistor or a microchip, right? So now, like microchips, they're complicated pieces of technology, but they still just need to be manufactured to certain quality specifications. But just as importantly, they need to be delivered to product developers, the people that are making these final products. In formats that easily enable enable them to incorporate this complicated piece of technology into the products that they're developing. So just like if you wanted to make a new electronic device, you don't have to first know how to make your own transistors, right? Process silicon, assemble those transistors onto a microchip, and then make that at scale at a cost that would enable the cost structure of your product that you're developing. That's really hard, right? So just making your final product is hard. You buy an off-the-shelf microchip from Motorola or Intel, and that takes 10 years of your product development cycle. And this really just exploded the computer industry, right, back in the 60s and 70s. But today, in regenerative medicine, if you're making cell therapy or much more complicated tissue engineered therapy, you have to, if you have to sell as any component of your final product, you have to know how to make your own microchip. The product development timelines are just immense, right? And so at Rooster Bio, the approach that we took, and nobody else is doing this yet, is we're providing living cells as essentially off the shelf, ready to go. You focus on building your product. Let us take this 10 years of supply chain, and we're offering these to product developers. So we're not doing therapies ourselves, right? That's not our strength. Our strength is cell manufacturing in formats that easily enable our customers to get their product into the clinic as quickly as possible. And our first customers are in the clinic. We've taken at least 5 years out of their product development timelines. This is going to accelerate the entire industry, and this needs to happen more, especially in tissue engineering. And I think the thing the slide that I really like that illustrates this, and it really overlaps a lot with what Dean was just showing, is this article from Gary Pisano, who's one of my favorite authors. He talks a lot about, he's a Harvard guy, he talks about manufacturing and how it drives innovation. And he borrowed this slide from these MIT economists back from the 70s. So across industries, right? This is phase of industry life is on the bottom. This is the product cycle of innovation. And on the left-hand margin is the rate of innovation that happens in these industries, regardless of industry, whether you're making cement, semiconductors, or stem cells. First, you have product innovations, right? It isn't until you actually have, oh, I need this product, right? And people need it, and they will pay for it. And it's then, only then, is there an investment in the manufacturing sciences. So after you get the product innovations, you know what you want to make. Then there are investments in the process sciences, the manufacturing sciences, and then you get a wave of process innovation. This is where cell therapy is right now. So when I got into industry, I went to cell therapy manufacturing, because then we had to figure out the cells before we figure out the tissues. And we are going through massive rates of innovation in manufacturing, scaling up, cost reducing, and getting these at a standardized quality. Still a long way to go, but luckily there are National Manufacturing Innovation Institutes that are investing in these manufacturing sciences as it relates to cells. One of them is Nimble, the other is BioFab USA, as it pertains to tissue, engineered tissues. But if there's one thing I can say is we do need more investment in the manufacturing sciences, because we cannot rely on getting our cellular raw materials for these engineered tissues from overseas. The U.S. needs to make sure that we own this component of the supply chain, right? That is really, really important. And then as you get into engineered tissues, so this article, about the billion cell construct, right? So what it is these are a log scale on the bottom. As you do basic biology on the left-hand side, it's what all the science has been working on for the last 100 years. You don't need that many cells. You need hundreds of cells or maybe millions of cells. But as you go up into the therapeutic threshold for organs, is in the tens of billions of cells. That's horribly expensive to get to. And so we're trying, as well as the field's trying, to work the cost out of the cellular component of this, right? And an illustration of this, I call this the technology roadmap for scalable cell manufacturing. And you may recognize these S curves. These are called the technology S curves. Clayton Christensen, 101, he writes on disruptive innovation. Started out with the microprocessor field, but every production technology is good for a log or two of productivity, at which stage it starts to top out, and you can't get any more out of that. So on the left-hand side, this is specifically for mesenchymal stem cells, and the take-home message is the title of the slide. The manufacturing platform, as it evolves, will drive economics of the living cellular components, right? And so on the left side is your lot size. Again, this is a log scale. And in the T-class production, that's what they use in academics. The scientists do this. If you need 10 million cells, 100 million cells, easy, not a big deal. But as you get towards needing 1 billion cells, those technologies really top out. You can't run a clinical trial if you're only making cells 1 billion at a time. And at which time you actually move to the next manufacturing platform, which is the multi-layer vessels. Easy to make 1 billion cells, 10 billion cells, really start to top out at 20, 30, 40 billion. And then if you really need to, and I personally consider commercially relevant manufacturing lot size to be north of 100 billion cells per lot. And the only way to do that is these single-use bioreactors, technology that was used in monoclonal antibody production, but a lot of manufacturing experiments need to happen in order to make this applicable to where the living cell is your product. Now, again, this dramatically impacts the economics of cell supply. So the metric that we follow in my part of the field, and I work with MSCs, mesenchymal stem cells, is the cost per million MSCs. But again, that's fine for cell therapy. As you get into tissues, now you have to think of cost per billion MSCs, okay? So when you're small scale making, when you only need 1 million cells, $100 per million cells is not a big deal. The NIH can support that. As you get into clinical trials, $10 per million is really the best we can do. Really, the majority of the field is still in 10 layers when you're in cellular therapy. And you get to this cost structure, and this may be fine for small scale production, but as you get to large scale and you're trying to make therapies for hundreds of thousands of patients, it is challenging. And that's not forgetting, pharmaceutical companies do need pharmaceutical margins, which take your manufacturing costs, multiply by 10, right? And so if you have $10 per million, which is now $10,000 per billion, right? There's not many indications that insurance companies are going to reimburse for $100,000, right? So the cost structure of tissue engineering is definitely broke, and really the only way to get that is with these bioreactors, and that's really going to be necessary for bioprinting and tissue engineering to be a commercially relevant industry. Now, just like Moore's Law did not, semiconductors did not top out in the 1970s like they thought it was, I really believe that in the next 5 to 10 years we will know how to get to tens of cents per million of cells. We'll still be maybe 5 to 10 years away from it. But over the next 10 years, once you have the cost structure of tens of cents per million of cells, right, then really we'll be seeing engineered organs and cellular technologies being even outside of the medical field. And so getting back to this slide, this is the last slide. The field is right here, but what this is good as we get the process innovations to really bring the cost of the cellular component of engineered tissues down, this really then drives the rate of innovation of these very complicated products. I use the iPhone also for a lot of metaphors, but I really think that engineered tissues are the technology that is going to require innovations in lots of different places. This is a phone, this is a GPS, this is a screen, this is a supercomputer as well. And it's going to take really all of these things to make tissue engineering a reality. And really, right now, the cells are 90% of the cost of these things. And once we get those down, then really the world is open. And that's what that I really believe that the United States needs to continue to invest in. So, thank you very much.
Thank you everyone for staying to the end. I'd like to make sure that we bring everything home from all what you hear today, from Dean, from David, and from John. I'm Claudia Zilberberg. I'm actually CEO of Afro-Biotech. I also wear a couple of other hats. I had a chance to perform together with Richard McFarland, the standard coordinating body, creating standards for this industry that now we can call an industry. That's what the standards for. And definitely became very active in this space. And talking about the cost, this calls to a little bit of understanding that the industry is real and really to stay right now. These numbers don't lie, and the numbers give us the opportunity to understand that this is becoming an industry. We need more technology in place, more standards in place, more workforce in place, and all the investment that we can to make it happen. So definitely more than 1,000 companies, a lot of money being invested their local economies and regional economies. So definitely it's not only a national endeavor, but also a regional endeavor as well. The idea is that now that we learn about cells and automation, we actually are part of the ecosystem, giving the cells what they need to enable them to do what they need to do in a scale and the quality that is needed to make it happen. Remember that all these products eventually will not have a chance to be sterilized at the end. Cells are not able to be sterilized and not either the tissues, so definitely the quality of the materials that are going to be used to manufacture these products are critical. And if we see a little bit of the supply chain and all the processes that are happening in a little bit more granular than what actually being shown earlier on, you know, the collection of the cells, the logistics that require the cells or tissues to be cryopreserved, and the manufacturing, taking it to the manufacturing site that usually is outside the collection place, and eventually, again, be able to deliver to the patient is quite critical. So actually, Akron decided to go ahead and develop quite a few cryomedias, preservation medias, and large-scale manufacturing of medias and growth factors that are needed for these cells to grow. Without that, all this machinery is not going to work. We have been active in the space, working together with different organizations, and actually you can see outside if you want to grab a piece of work that we did together, and Richard is part of it as well, on manufacturing cell therapies with the National Academy of Science, understanding what are the challenges, the risks that the industry brings to us, and why we are here in this room together trying to make it happen. Definitely is not one only stakeholder, many are involved in this endeavor. And understanding also that the business model has to work. So sometimes this delivery of the cells or manufacturing of the cells needs to be close to home. So we need to keep it within our geographies. And last but not least, understanding the tissue engineering actually workflow is a little bit more complex than the cells that John related a few minutes ago, where tissues are needed to be put, the cells are needed to be put into eventually scaffolds, have combinational products, and have regulatory agencies understand the complexity that this comes with it. Sometimes it's not necessarily an organ that we transplanted, but a de novo organ that needs to use scaffolds, cells, proteins, and cryopreservation media. So again, Akron has been hugely involved in developing, together with our fabulous saying, because actually we became to be one of the first members of this group, and the first ones to receive a grant and to do the cost share with this innovation of cryopreservation of tissues to be able to help in the process flow of this kind of work. Akron is a company that is based in the U.S., in Florida. It's home. It's not a small business anymore. It's growing, and it's growing with the industry. It's been 12 years in the making, and we really are proud of seeing the growth of the industry as we speak today, developing these ancillary materials with the quality standards that are needed to make it happen. So here we hear about the automation, the cells, and the components that are needed to make all of this happen. Thank you for the opportunity.
I don't know about you, but I'm sitting here saying, wow, this is really something. Let me make a couple of comments before we open for questions. The mission of ASME is to disseminate technical knowledge to improve quality of life. And I was thinking, this is it. This is the best example of improving quality of life. Another comment I'd like to make is that bringing all these companies and stakeholders together and having them all focus on one issue, one purpose, that's your mission, and that is great. This is how it can occur. Well, I want to thank our speakers, our panel members, and I want to invite them to please come and sit here. And then I invite everyone to, if you have any questions, please state your question clearly. And if the question is for one of the panel members, please state so. And if the question is for all of them, I'll also say that as well. So the floor is open for questions.
Hello? Okay, okay. So this is for Dean, but others can chime in too. So what is the goal for achieving the first organ? I mean, is it in 2 years, 5 years? And what is the organ that you guys are shooting for?
Let me officially start by saying I don't know you very well, but I don't engage you. That's the toughest possible question, and yet it's the most reasonable one. When we started, and with no false modesty, I told our friends at DOD, I don't know anything about the biology. I don't know how many any of these things are, and how much science fiction is still left to the science. But I'll try to bring the engineering community together to answer some of these questions. And almost from day one, we talked to the clinical community, and we find, and if you can't help the engineers make a matrix, and we look at everything, look at everything. I said, what's going to happen is we're going to figure out there's some organ that is the one that is needed the most because we can't sustain people without access to it. We can give people, for instance, dialysis while you wait for a kidney, but you can't keep people alive that don't have liver function because there's no substitute for that. Okay, so then liver should be higher because they eat it more, they'll die. But it's a small number. Oh, but it's hard to do. Oh. And when we finish making a matrix of 10 or 15 or 20 different organs that we all need, the 20 different organs, talking to the clinical community, the research community, 20 different organs, there were 21 different reasons why this one should be the first. And then we started looking at level of difficulty, cost of development, risk, and we kept trying to find the one that would be this is where we start. We'll grow from there. And as we sit here now, nearly 2 years later, there's at least one passionate researcher that's still swearing that their organ is the one that's most important, most straightforward, closest to reality. So we don't have a good answer. But what we did do was we found the commonality, the things that most of whether that on the clinical side or the engineering or the manufacturing side, they all need closed loop control systems on sealed bioreactors that can't be screwed out by contamination of the environment. They all need so many basic things that none of them have. We said, you know what? Instead of picking the first organ and hoping to get it right and hoping it's doable, why don't we instead figure out what are the common things that everybody needs, do those first, hand them out to all of our constituents and let them all know. And whether you need eyeballs or toenails, you figure it out. We'll just get the standardized platforms up and running as quickly as possible so that everybody can move at the fastest rate they can based on the limitations. And that's what we're doing. If you ask me, and I'm not the clinical side, I'd say getting whole organs, whether it's the liver or the lung, what we don't think about, ready for transplant, that's the final step. I think we'll see expansion of cells, as you heard, and they're plenty valuable. They can synthetic blood, but making cells, making flat tissue, making tubular tissue, like taking the flat tissue and rolling it up, making an esophagus, making a piece of tissue to put on the heart. I'd say it'll be making cells, making tissues, making collagen to make skin and bone, and then you'll make subsystems of organs, and then finally we'll make whole organs. If you then ask what's the first one that will get through the FDA, we're going to go grovel and beg whatever at the FDA to hopefully help us expedite some of those early ones to incentivize people to do more. I would be very disappointed, I love the risk of saying this, I would be very disappointed if we don't have at least some manufactured scalable output from some of our constituents going through clinical trials by the end of the 5 years that I promised the DOD we would do, and we're already 2 years in.
how should we invest as a country in securing the supply chain so that we can own more of that industry inside the United States?
That's a great question. And I would say up until Nimble and BioFab USA were funded, we were well behind Canada and Australia, and who were putting tens of millions of dollars into various pre-competitive type organizations like CCRM. I forget the name of the Australian one, but many countries are investing in basically many of the platform technologies and the infrastructure to help then that industry get a springboard forward. I think that these NMIIs are a great start. And so in the supply chain, like I would say that the majority of things that make the cells the most expensive are made by the Acrons of the world, right? So and it's because their reagents are expensive, right? The growth factors, the matrices, everything has significant costs. Now, one of the things that I definitely like to bring forward is, and there's a great book out there called Biology is Technology, and it's that biology is progressing at the pace that information technology did. We knew how to process silica well before we knew what a gene was, right? So we're just a few decades behind. But we are seeing these log improvements in scale, log improvements in cost, log improvements in power. And we have seen that in antibody production and protein production. And so I do believe that over decades, we will see these costs come down to the point that the cost will then get worked out of the cells, and then the cost will get worked out of the tissues. So this will take time. And I think that while these NMIIs are on the cells, one of the I sit on a working group on the industry committee for cell manufacturing technology, which is from Georgia Tech and Wisconsin, two academic institutions that are driving cell manufacturing technologies. And we're realizing that we're investing in really understanding manufacturing of cells, but then the really big cost driver is the reagents. And so actually getting in a little bit deeper into the supply chain, into the growth factors, into the viruses, into the tissue engineering scaffolds, because that's really, really expensive. If we bring the cost of all these things down to a log, then I think that helps bring the cells down. And I think we have technology to do $1 per million cells. We need 10 cents per million cells, right? Or $100 per billion. I mean, that is just the world really opens up. And so I would say that really owning this supply chain, and much of that supply chain is ex-US of growth factors and media, and so bringing a little bit more of that in, I think would be one of my first.
I think your question is very specifically along the line about where do we stand compared to China, for instance. I would say a cautionary tale, especially for the folks in Washington. I just came back a couple of days ago, I had 2 weeks in China. Make no mistake, the Chinese have figured out this is the next big thing. And every technology ever developed by humanity goes 2 ways. It's a tool to improve quality of life, and it's a weapon. This is no different. And it will be a tool for healthcare. It's an obvious weapon, bioterrorism, etc. It's also an economic weapon. And I think the Chinese have a couple of advantages right now. Number one, the U.S. has been at the leading edge of every technology development in the Industrial Revolution, steam engine, gas turbine, nuclear, you name it. We're starting with an even playing field now, but they're much bigger than we are people. And they have another advantage. They are not bound by what we consider the appropriate ethical barriers to do experimentation. I'm not suggesting we like their system, but this country and the leadership of this country, particularly the DOD, I think, needs to understand that while we're doing what we're doing at the pace we're doing it, there's 1.5 billion people in a country that's obsessed with this opportunity. They're moving very quickly, and I don't think they or any other country reason that I happen to be glad that it's the DOD driving this one and not some of our other institutions. But the rest of the government of this country gotta understand this is not an academic opportunity. This is a very serious issue.
Agreed.
I do have a question that extends this ecosystem. Gene, you mentioned, the future, the Silicon Valley. So this question is really, and I noticed how you gave the very best non-answer possible to Andy's question, because there's so much we don't know. You don't want to be tied down to, yes, I can print off my kidney in 20 years. This is a thought experiment. You are violently successful with BioFab, and Nimble and BioFab are hugely successful, exceeding all its goals. Just to get a sense, are we talking one ecosystem for the United States, or I'm seeing that here's Boca Raton, Florida, Frederick, Maryland, Milwaukee, Wisconsin, and Manchester, New Hampshire. Are we talking about 20 years from now, thought experiment, so all the caveats there, you're wildly successful. Is this a $40 billion market with a single ecosystem somewhere in the United States, or is this a $400 billion market with ecosystems all around the country? Where do you think the future is?
First of all, 20 years from today, the market for curing diseases of an ever-aging population, the market will be far larger than any market we've seen today, including automotive or something like that. And by the way, if it's not, we will bankrupt ourselves to take care of the ever-larger group of people that need care. And by the way, I've never met a person that likes their chronic care. It's not like after we spend 20% of the GDP, we're happy. I've never seen one of our patients say, can't wait for my next treatment in that dialysis center. I've never seen a kid that can't wait to prick his or her finger again to check the glucose before they can have ice cream. That kid doesn't want to have diabetes. That adult doesn't want to need dialysis. These solutions, lower costs, improve quality of life, they're wins across everything once we get there. And it's a way bigger opportunity than any other industry. As such, it will be medicine practiced everywhere, not in one place. In the same way that, yeah, Silicon Valley is where it is, but people develop software everywhere, people do apps everywhere, people are making electronic systems everywhere. There will be a global distributed industry around this. My point about creating a Silicon Valley, and the same way we created the Detroit complex, until you get rid of all the risks and do all the hard work that no one company is going to do on their own, until you get an established baseline, until ASME and IEEE and the FDA and this create the standards that everybody can use, there's got to be a central way to do this. You can't build an industry with a couple of little startups doing things differently. And all I've been suggesting is pick a place to do it. Now, I happen to be a little bit partial to, let's take a nice new place where we've got our governor and our senators and this legacy of our really, I'm saying, hey, since it doesn't exist anywhere yet, let's put it here. We're not going to go out and compete in the basic medical research with the Harvards and Stanfords and UCSDs, but we're small compared to them, but we're big compared to nothing. There is no industry yet, so what we need is to quickly bring everybody together, create the baseline, and then let it grow. We're in the mode now of creating that baseline. We need all the different engineering disciplines. We need all the open-minded, creative people from every aspect of where we are to get us to where we want to go. And we will create in some place the core of the regenerative medicine Silicon Valley of the world. I'd like to be mentioned.
Well, it's basically creating the supply chain that you need, and at least locally first.
I have a question to switch gears just a little bit, which is I guess more the automation side. We've been using the example of iPhones, transistors, things like that, but transistors are very defined, right? We know exactly what all those 4 billion transistors are for and what they do. Cells, while they are kind of a microchip or a mini computer in themselves, we don't actually know what all the levers and knobs and switches inside a cell do. So I guess this would be kind of a question for everybody, but maybe John and David primarily. how close are we to, I guess, defining those levers and switches that we need to be able to push? And then on the other side of that token, how well are we able to monitor those levers and switches that we need to monitor?
Sure. I mean, so I think we're learning more and more every day, right? And as we apply big data and AI to some of these challenges, I think that the pace of learning is also increasing, right? And that's really, really important. And while we may not know everything in the next 10 years, I think we're going to know so much in the next 20 to 30 years that that we will be close to full definition of what's going on inside of a cell. As I mean, that's getting us very close to the singularity, right? So who knows what's going to what the world's going to be like then? But I really think that it's this convergent technology again, like kind of like the iPhone, where all these different things are happening at the same time. The advancements in bioinformatics and AI and really understanding, and then the sensors, right? They're getting better. I mean, people that are planning building sensors and putting them inside a cell so that you can figure out what's going on there. Now that's at the super duper research. That's only been the last 5 years. But you know what? 15 years, that's a product that people are actually using potentially in medical devices. So I just think this concept that the pace of innovation is not a linear function. It is a logarithmic function, an exponential function, and it's just going to continue to accelerate. In 20, 30 years, right? At least in my lifetime, we are going to be as close to full knowledge as we need to be and we'll know how to manufacture things. I mean, we're going to go from concept, oh, wouldn't this be a great idea, to a product in just a few days. I mean, rapid prototyping of biological solutions is more than 10 years away, but it's not that much farther. So I think of it in that we're really not that far away today. Are we there today? Are we there today? No, but it's really not that far.
I'll speak to the monitoring portion. So the monitoring portion really is the most difficult hurdle we see in scaling through production. If we have somebody that's able to complete a process and is able to monitor it, taking that and scaling it is documenting what they've done, what the process steps are, and that involves measurement. And that's really what we're lacking today in many cases, which is why we have people that are skilled researchers that have to work with those items today in order to bring back. We want to be able to take it to the situation where we have detailed measurements are possible, be able to define the process, and have people that are less skilled to be able to actually manufacture. And that's going to be the key. And that's going to be some work that's been done in the next few years to scale.
I just want to add to all these comments is that the interesting moment that we are today is that the crossover of different technologies and different disciplines that are working together. The biology, the mathematics, the physics, the chemistry is just unbelievable, that crossover that we're having right now. And that is what we are good at. That's what the US is good at. Sometimes, massive economies like China, they work on silos working in one thing at a time. We have the creativity to put things together, and that's where is our forte, and that's what we need to talk about.
What is really important in manufacturing institutes, and this is a very good example, is the collaboration. Collaboration between government, industry, and academia. Collaboration between all disciplines that you would need, and everyone focuses on one problem. On average, everyone says that it takes 25 to 35 years for a product to become commercialized after it begins. So basically, what everyone is trying to do, and actually all the manufacturing USA institutes, is trying to reduce that 25-35 year cycle to as short as possible. And I think in this case, a few days, if possible. Because sometimes you need it, sometimes you only have to do it. This is great. We still have time for questions.
yes, maintaining dominance in this supply chain, but can you speak a little bit to how that would happen? I mean, this institute, and it's not gonna last forever, and somehow you're gonna marketize this stuff. What do you see? What's the roadmap for the U.S. control of this?
Manufacturing, for manufacturing capacity is quite important. Manufacturing in the U.S., bringing home all that technology needed home. That's what it's all about.
And so I would say, Brewster Brown is a good example. We've got a couple of biofab grants, and as well as an MTech grant, which is also DOE funded specifically in scale-up manufacturing. So creating 50-liter, so specifically this MTech program, we got 3 million out of 8 million total with other collaborators to generate, to develop. It's that process development, which is right in the chasm that underneath the slide that doesn't get funded very often. To develop a 50-liter bioreactor for fully xeno-free, which means a regulatory friendly profile, for these mesenchymal stem cells. That's for wounded warrior applications. And so that 3 million, we're a small company. We've raised less than 10 million total from investors, right? 3 million is a really big amount of non-dilutive funding specifically to help us develop what that manufacturing process is. And because every time we run a 50-liter bioreactor, it's over $200,000 in just the bill of materials, the materials that go into that. And there's no way we could have invested in that manufacturing process without this government funding, which is going towards the manufacturing sciences right now. And then what we're doing is we're helping to use that to lower our cost of goods, so we can now bring a brand new cost structure to our customers. And then we essentially, our product is we actually kind of give that manufacturing process away to the therapeutic companies that want to run a therapeutic company. And then that's kind of the razor of our business model. And then we sell the cell banks and the cell culture media that go into that, so that they can now manufacture at the scale, taking out the 3 to 5 years that it would typically take to develop that, turning that to zero, taking that time, that $3 million, and this is again out of $8 million total thing, so taking probably $8 to $10 million out of their cost. They have to raise less money from the venture capitalists. They have a brand new business model now that has a better return on investment. And they get to the clinic faster. But for them from the supply chain, we are part of the supply chain. We're not a therapeutic company. Now that is a Frederick-based business. We're selling our products all around the globe. And so we want to be that key piece of the supply chain from the cell side. So I think as these go and fund the supply chain companies to help them bring to market better reagents and things that are needed to manufacture the drugs, the cells and the tissues, then that's how we own the supply chain. So essentially, you typically don't invest in manufacturing sciences. In the you look at the biopharmaceutical industry. We didn't really know how to manufacture monoclonal antibodies very well until we got the first blockbuster drug to market in the early 90s, right? It was EPO, right? We were making a really low-tech manufacturing process. Once you have $1 billion product, now these companies can invest tens of millions and hundreds of millions in the manufacturing. Now we're 2 logs, if not 3 logs, higher in productivity in generating therapeutic proteins at a much lower cost. But you require that first $1 billion drug on the market before you can invest in the manufacturing sciences. Now the U.S. is investing in some of the manufacturing sciences. Before we have a $1 billion drug, that's essentially accelerating the industry, making sure that the U.S. is. That's kind of how I think the philosophy is. I'm not sure if it's that sophisticated at the NIH and the DOE levels, but that's kind of how I see it playing forward, and definitely the continued investment in the manufacturing of the supply chain, so we can get our therapeutic companies to market faster than they have once they're to market. They're in the cost structure that they actually have a business, which doesn't always happen in regenerative medicine or I guess any new industry. I think that's what we need to accelerate.
Just ask a question.